So we have a flat metal plate and we have it located at a coordinate plane. And the temperature of the plate in degrees Fahrenheit at any given point x, y is given by this two variable function in terms of x and y. So they're asking us to find the minimum temperature and where it occurs. Is there a maximum temperature? Well, we'll figure out. Alright, so the good thing about this problem is that we already start with a two variable function, not a three variable function for which we would need a constraint to solve for that and then substitute, do the problem, and then go back, substitute for that constraint to get that maximum or minimum depending on what we obtain. So we can go ahead and find the partial derivatives t with respect x. So that's 2x minus 8 and t sub y that's 4y plus 4, and we need to set these partials equal to 0 to get the critical value or the critical point in this case. So 2x minus 8 equals to 0 and 4y plus 4 equals to negative 1. So that means 2x equals to 8 and 4y equals, oh, actually 0.
Finishing with the last one.
4y equals to negative 4. That means y equals to negative 1 and x equals to 4. So the critical value here is, or the critical point is the point, the order pair for negative 1. Alright? So we need to determine whether that point will give us a maximum or a minimum. So let's see. So we need to find the second partial. So the partial twice with respect x. So that's the derivative of this expression, of this function. So that's 2. T double y. That's 4. And t that was once differentiated with respect x, and now we do it with respect y. So the one that we differentiate with respect x, differentiated with respect to y. Since there's no y's at all, everything is constant. The derivative of a constant equals to 0. So I think we're ready to compute the d quantity, which is, well, I'm going to write down the formula to refresh on the formulas from last time. So that's txx times ty minus txy quantity squared, which, I mean, in this case we're using big T of x, so the general formula is for f of x, so it's the same thing. And in this case, well, that's 2 times 4 minus 0 squared, that's 8. So what do we have? Number 1, we see that d is greater than 0, it's a positive value, and also t double x, it's also greater than 0. So in this case, isn't that a minimum? I mean, they were telling us that minimum value, right? So now they're asking us to find that minimum value. So all we have to do is plug in this point over here in the original function, that is t of xy. Oh, t of, not xy, it's t of 4 negative 1. That's a 4 squared plus 2 times negative 1 squared minus 8 times x, which is 4, plus 4 times negative 1. And simplifying all this, we should get negative 18. But now that we have the final result, this is where we will put the units together. In this case, degrees Fahrenheit. Alright? So, is there a maximum temperature? Well, I mean, let's look at the function. Notice the original function, x squared plus 2y squared minus x squared plus 4y. Well, let's consider only the higher order terms, in this case the square terms. Those look like parabolas, right? So it's a parabola in the x direction and another parabola in the y direction. The couple of linear terms will only give a sense of translation, of shifting, but it's still going to be, I mean, we're going to have like a paraboloid, like an ellipsoid, I mean a paraboloid in the form of with a base of an ellipse because of the different coefficients multiplying x squared and y squared. So since this looks like a parabola, well, a parabola never has a maximum. I mean, it's just infinity pretty much, right? Now let's see. What is the value of the gradient at the point you found in part A? Well, so let's find the gradient. Well, in fact, we don't even need to find the gradient. So nabla of t, that's tx, ty. We already found the first partial derivatives. And well, this means nabla of t equals 2x minus 8 for y plus 4. And well, if we evaluate the gradient at the point 4, negative 1, that's 2 times 4 minus 8, 4 times 2, 4 times negative 1, that's a plus 4. But what's this? Isn't it a zero vector? And well, they're actually asking us for the value of the gradient, or the magnitude of the gradient, right? It's kind of not clear what do we mean by the value. So the gradient, it's a vector, right? It's a vector that stores two pieces of information: the rate of change in the x direction and the rate of change in the y direction. And also that gives us the direction of steepest descent or ascent depending on the sign. So if we get the magnitude of nabla t, that's the magnitude, 0 squared plus 0 squared. Well, what is that going to represent anyway? I mean, what we're doing in this case is substituting the critical values in the derivative. That's going to give us a 0 because this is the point where the rate of change, where the rate of change is 0, and that occurs when we have a maximum or a minimum point. All right, so that's ultimately the rate of change. All right.